So this is the CS3214 Project 3 memory allocator, aka Malloc, and this is the help session. So we were talking with the CS3214 staff, and I think we're only going to do one help session. This is it. We're going to put a video on the course website if any of your friends haven't attended this help session. And we are ideally going to do another FAQ session, probably next week early on, just so people have time to get all the information, gather up their questions, and hopefully ask questions about either the heap inspector, which I'll talk about, or the memory allocator. And I'm kind of happy I have some more TAs in this room as well. So if you guys trip me up on any questions, hopefully the other TAs will be able to help out as well. But without further ado, let's get started. So here's a brief overview as to the topics we're going to talk about. By the way, before I go any further, can everyone hear me all right?
Yep.
Perfect. Okay, so here's the topics that we're going to talk about. We're going to talk about an overview of the memory management on most modern systems, basics in getting started for this project, what the project structure is, GNU perfutils and other tools. And by the way, these will help you debug performance issues, logistics and grades, testing framework, and last but not least, the heap inspector tool, which is brand new this semester. So let's go into the overview of memory management. This is what most modern systems generally adopt in terms of memory management for programs and processes. So what we see here is kernel memory, and we have a stack, heap, uninitialized data, initialized data, and text. The most important things for this project is the heap and the stack. The heap grows upwards and the stack grows downwards. And they all grow towards each other in this one unallocated memory area. And by the way, when you do this project, you're going to have to keep in mind this this function called mem_sbrk, which can actually change your heap's end location. So keep that in mind. We'll talk about that a little bit later, but this is the general structure as to what processes in memory, what they look like. So here is the heap. It's persistent unmanaged memory granted to processes, and it'll be coupled with a garbage collector sometimes. In the case with libc and Malloc and free, it's all unmanaged, meaning you have to do all of the memory allocations and all of the frees by yourself, which I'm sure you've realized. Other languages like Java have an automatic memory collector or garbage collector, where you don't actually have to worry about freeing any object that you allocate in the heap. So there's a few terminologies you should know. If you hold on to memory for too long, you have something called a memory leak. Or if you free memory too early, which I'm sure some of you may have run into in Project 2, you run into something called a memory corruption. One of the things about this project is that you can't use tools like Valgrind to easily diagnose issues like you did in Project 1 and Project 2. So just keep that in mind early on as you're working. So that is a brief overview of the heap. Next, let's talk about BRK and SBRK. These are the functions I talked about a little bit earlier. SBRK is a function to increase the size of the data segment, and BRK is a function to set the ending address of the data segment. If you recall from the first dpipe exercise, when you ran strace on the program, you might have seen a lot of this stuff, mmap, which by the way is talked about in lecture, and then this BRK syscall, which actually increases the size of the data segment. So if we actually go to our first diagram here, we can tell BRK to increase the whole bounds of this process. And that's what BRK can do for us. And this is commonly used in conjunction with something, by the way, like mmap, like you see in this strace output. Like I said, you will be using a similar derivative function called mem_sbrk when you're doing this project. So the goal of this project is to basically consider the time versus space trade-off in many different allocators. There's actually a lot of allocators out there in the wild. The most common one, which I'm sure you all are familiar with, is the libc Malloc implementation. This is the one that comes with the C compiler, quote unquote. And this is your general Malloc and free operations that you all love so much. So another one is Google's TC Malloc, which is actually a very, very fast Malloc implementation. And one thing you all will realize as you're starting to work on a memory allocator is how specialized some of these Malloc implementations can be. And by the way, does anyone have any questions as to anything I just talked about right now? Let's see if I can get the chat window up so I can follow along. All right. Doesn't look like anyone has any questions right now, so I'm going to move on to the next section. I will also have a Q&A session at the end of this in case anyone has some questions for me. But the first thing to do for this project is to fork the repo, the git.cs.vt.edu Malloc lab repo, as you did in Project 1 and Project 2, and set it to private. It's going to be similar to the shell project and Project 2, where we actually grade on your Git usage. So recall or remember to use Git repositories with this project. And by the way, we've had some groups that make their own group within GitLab. We won't be able to see your project if you make a GitLab group. So just fork it into your own namespace as opposed to creating a group. That'll save everyone a lot of headache. Here are some of the functions that you need to implement for your own memory allocator. You will actually write each of these functions, and they all have a similar convention to that of Malloc, like the Malloc that you're familiar with. Except for this one, init. This is not something that's in libc's Malloc, but we will be calling this function inside of your code. So there's init, which initializes your memory manager. And by the way, that might do stuff like initialize any free lists you might have, or do any other initialization, like call sbrk. Malloc is the function to allocate new memory inside of your memory allocator. And you just simply give it a size, just like the regular Malloc. And it returns a pointer to freshly allocated memory. free does the opposite. You give it a pointer and it frees that memory, just like how free does in libc. And then realloc, of course, this, by the way, might not be a function that you all are familiar with. This reallocates memory, maybe at the same pointer address, maybe at a different pointer address, and it either increases or decreases the size of an allocation. So this, like I said, is something you may not be familiar with. All you need to do is just pass it a pointer to a previous allocated block, and the size you want to resize it to, whether it be bigger or smaller than what you had previously, and it'll return either the same pointer or a new pointer to a block of memory. And like the real Malloc, your allocator must be able to handle a variety of allocation sizes, whether that be only like 10 bytes or 10,000 bytes. So you just need to count various different possibilities when coding this project. All right, so here is how you get started. You're going to be writing a file called mm.c, and you are potentially going to be writing a lot of helper functions to perform specific pointer math. And this makes debugging significantly easier. We actually have an implementation called mm-gback-implicit.c. And if you look at that, it's a fully functional memory allocator that uses implicit blocks. And you can use that as sort of a baseline for your implementation. And we'll, by the way, go over that at the end, remind me, and I'll go over that file. Here are some of the provided functions that you can call. These are all in, I believe, memlib.c and memlib.h, which is in the provided base repo. We have mem-sbrk, which is what we talked about earlier. This increases the process size and allows you to essentially extend your heap. So this is what you would call if you want to extend your heap. The second one returns an address of the first heap byte, mem-heap-low. This just returns a pointer to the beginning of the heap. And the second, or the last function, returns the address of the last heap byte, mem-heap-high. These are all functions you may want to call in your code. And then we have some more. Mem-heap-size, this returns the size of your live heap. And then mem-page-size returns the system page in bytes, 4K by default on Linux systems, although I have seen it different on other machines, I think. So those are all the provided functions. This is what we talked about a bit earlier, mmgback implicit.c. A sample solution, which might be a good starting point. So you need to be mindful of all the different pointer arithmetic that you're going to be doing inside of the Malloc code. And the mmg back implicit file has a lot of these already done for you, a lot of functions to do some pointer arithmetic done for you. And like I said, this is a perfect baseline for getting started on your project, and it'll help you understand memory allocators a little bit better. So without further ado, let's talk about some strategies for implementing Malloc Lab. What we're going to talk about right now is something called an explicit list. So implicit lists are basically you have a list of blocks, whether they be free or allocated. And in order to allocate or free blocks, in the case of allocation, you go through each of your blocks on your heap, and you just find the first free block available that is the size that you need to allocate. This is very inefficient because if you want to do an operation like Malloc, it would be O of n. You would need to traverse a lot of the blocks on top of your heap in order to find the block that's big enough to support your Malloc operation. So implicit lists are not necessarily the best solution for a memory allocator, which might do hundreds of thousands of memory allocations every second. So instead, we suggest using something like an explicit list, a segregated free list, or a RB tree, any of those strategies to make your memory allocator. This is what an explicit free list looks like. So you have a bunch of free blocks in your heap, and we use a linked list data structure to link all of the free blocks together. And this is what it could look like. You might have a free block here, a header and a footer, and this is the list element associated with the linked list. And then maybe you might have some allocated blocks in the middle here. We don't really care about the allocated blocks. All we know is that our list element is pointed to the next free block, like so. And if we want to traverse all the free blocks, we don't have to go through all of the allocated blocks, which significantly cuts down on the time required to allocate memory. So that's essentially how explicit lists work. Next, we're going to talk about alignment inside of Malloc Lab. So one of the things to note is that, well, I'm sure the first thing you're wondering is what is a block? Like I keep talking about allocated blocks and free blocks. What's the difference between those? An allocated block is simply has a header on that block. And it might tell you like the size of the block and whether or not it's in use. So that's what the block header is. In the case of an implicit list, that's literally the only structure we have. In fact, let me deviate over to the GBAC implicit code, and we can walk through that real quick. So here is our boundary tag. This is essentially the header to our block, if the block is in use and how big it is. And this is the definition for how a block is structured. So we have the boundary tag that we just looked at, which has the size and if it's in use or not. And then we have the payload. This syntax might also look a little bit weird. It says char payload 0. This essentially means give a pointer to the start of this address right here, char payload 0. So it doesn't actually allocate an array of any size here. It just provides a pointer to where our block starts after the header block. So that's essentially what it looks like in the implicit list. You just simply have a block, and then right after you have the payload. And it looks very similar, by the way, to that of an explicit free list. The difference is your explicit free list, instead of the payload, is going to have a list element that could be used to link the other free lists with. That was a quick tangent, but let's talk about alignment of these blocks. So with Malloc and free and libc, all of the blocks are aligned to 16 bytes, meaning if you're looking at the hex addresses, they'll end in 0. So you need to think about alignment when you are returning your allocated blocks here, because we don't want to get a block back from your malloc operation that's not aligned to 16 bytes. So what you need to do is you need to think about that when designing your memory allocator. You need to think about where your blocks will start. They should start something like this. If your boundary tag is 4 bytes, they should start at 12 mod 16. And then this is your boundary tag, which is 4 bytes. And then this is all of your payload right here, which I said should be aligned to 16 bytes. So then after that, you have a footer to the block. One thing I've neglected to mention is every block has a header and a footer, where the header is 4 bytes and the footer is 4 bytes, and these are exactly the same. This just makes it easier to traverse your linked lists. So as I was saying, every malloc operation needs to return a payload aligned to 16 bytes. So just keep that in mind as you're designing your malloc implementation. And one way you can be ensured that all your payloads are aligned to 16 bytes is if you put a bunch of assert statements in your code, and we'll go over that in a bit. Let's talk about something called fragmentation and coalescing. By the way, these are all topics that are in the lectures as well. So if I don't explain it well, feel free to look at any of the memory management lectures, and they'll talk about fragmentation and coalescing as well. So imagine we have a free block of size 128, like in this example. And like I said, it's got a header and a footer. And there's another block here that has a header and a footer. This is all allocated, let's say. So the user wants to make a 16-byte malloc code. So what the allocator will do is it finds a free block, and it essentially allocates the either the beginning or the end of the free block, depending on what you want your implementation to do. And these 16 bytes will be allocated. There may be, by the way, some padding within the allocated block to ensure that the next free block is, or the next allocated block has its payload aligned. But essentially, in this case, when we allocate a 16-byte block, we actually need to split this free block in half, this free block of size 128, so that we have enough bytes for the allocated payload here and the padding. And we need to ensure that every other block, his alignment is still correct. So that's one of the things I was talking about earlier. That's an important consideration you need to make in your malloc implementation. So essentially, another thing we need to think about is something called coalescing. So imagine a call to free puts a free block directly adjacent to another free block, like so. So we have these two allocated blocks that one of them got freed and another one got freed, and now they're next to each other. So in a case like this, we can actually increase the size of a free block by combining these together. So instead of 2 free blocks, we can have 1 free block if we detect that they're right next to each other. And essentially, notice that the footer here and the header here disappear, and then we have a whole free block, like so. Again, these are all strategies discussed in lecture as well, in the first memory lecture. So be sure to take a look at that if you're confused about these strategies. Before I continue, does anyone have any questions as to how any of that works?
Yeah, I do have a question.
Okay.
So in terms of like the fragmentation and stuff, I'm not sure if you had mentioned it, but are we just starting with like one giant free block, and then when we're mallocing, we just fragment that block? I guess, like you had mentioned.
You can do a bunch of strategies. One strategy is, like you mentioned, starting out with a giant free block, and like it could be like 4096 bytes big or whatever. And essentially, you start out with that big free block, and then when you do like a subsequent malloc operation, for instance, you just split that big free block into like a smaller allocated block, and of course your larger, I mean, still smaller a free block once you allocate that. So that's one strategy. Another thing you could do is you could you could start out with 0 free blocks, but when you do something like Malloc, you have to make an SBRK call and ensure your heap is big enough, and just insert an allocated block in there. I think that would work as well. Does that kind of answer your question?
Yeah, that makes sense. Thanks.
Okay, any other questions regarding anything I just talked about?
I have a question.
Mhm.
So you said that a realloc isn't guaranteed to return the same pointer. Is this because sometimes it's more efficient to just coalesce or like combine the block with the next block so you can just append the new information onto there?
So that's a good question. The reason why realloc might not return the same pointer is not for that reason necessarily, but because there might be an allocated block after this realloc block. So if you consider, for instance, we have an allocated block of size, let's say 512, and right after that block inside of memory, you have another allocated block of size 1024. You don't want to do anything to that already allocated block because that might be used by userland code still. So instead, in the case of realloc, instead of like making any changes to the next allocated block, what you should do instead is free the block associated with the thing you're trying to reallocate and find another place inside your heap to return a new pointer to. So it basically has to do with not wanting to interfere with any of the adjacent allocated blocks, if that makes sense. Does that answer your question?
Yeah, it does.
Okay. Any other questions regarding any of this stuff? All right, and then without further ado, let's move on to the next section. So we're going to talk about the project structure and different suggestions to take in this code. So the first suggestion I would have is you need to consider the performance implications from the start of the project. One of the most heavily graded things in this project is performance. So you need to ensure that your memory allocator is very fast and very space efficient. And these are all considerations you need to make from day one. So can I only include the structure in the tag in this certain situations? Do I have all the fields I need? Am I willing to trade space for performance here? These are all considerations you need to make. Another thing I suggest using a lot of is these assert statements. So you may or may not have used assert statements before. I believe in project 2, I recommended to some groups using assert statements to catch some bugs. But essentially a C assert is just like it is in Java. I don't know if you guys remember making JUnit tests from the 2114 or 3114, but it's similar in that the program will essentially segfault or fail when it reaches one of these assert statements and the condition passed into the assert fails. So if you put a lot of these into your code and you make asserts, for instance, is my payload aligned, and a bunch of different other criteria, or what is the minimum word size? If you just spread out your assert statements liberally in your code, it has the potential for catching a lot of errors right as they happen. Don't be afraid to put a bunch of these in there. Trust me, this will save you a ton of time in the long run. Get used to this. And make sure you explicitly state the pre and post conditions. And you might also have a lot of headache if you put the wrong condition inside of the assert statement. So make sure your conditions are correct as well. So that's what I just talked about. This basically figures out where the bug occurs rather than a side effect of the bug. So what that means is basically, do you want the program to segfault, 2 or 3 allocations after the bug occurs, or do you want it to segfault right away when the bug occurs? And you want the former. You want it to segfault right away when the error occurs, which is why you should put as many assert statements in your code as possible. So here are some suggestions. We have, by the way, some helper functions I mentioned inside the mmg back implicit file. You can use some of these functions in your own code. Feel free to copy and paste whatever functions you need. A lot of these functions have pointer arithmetic magic in there. And this is basically a lot of what the memory allocator needs to do. It needs to do a lot of pointer arithmetic. So what that means is you basically need to ensure that you are returning the right payload bytes. You're making sure that all of your padding is correct, and all of that requires a bunch of pointer arithmetic. Also, use a profile such as gprof. You haven't used gprof in this class before, but this will help you understand which functions in your code are taking the most amount of time when you're trying to optimize the memory allocator for performance. Another thing I would do is start early and try many different implementation strategies. Earlier, I talked about the implicit list, which, by the way, you can't just resubmit Dr. Back's implicit list file. I wish it were that easy 100, but you can't just do that, sadly. So you have to experiment with things like explicit free lists and things like segregated free lists. And these are all strategies covered within the memory allocator slides. By the way, one of the things I noticed is that many students opt for the segregated free list approach, which I think is the easiest strategy to go with. That'll give you the most amount of performance points. There is another strategy, RB trees. I would not go there unless you want to challenge yourself or you want a really performance solution. But segregated free lists in general should give you the performance you need for this project. So here is another suggestion. You need to make sure that, like I said earlier, all the payload bytes are aligned correctly. This is a macro that I think we put inside of the provided implicit C file that can essentially align some bytes to a particular alignment. Another thing to be careful about, and this is something that gets a lot of students, is to be careful about the linked list approach. So if your memory allocator is buggy, it has potential to overwrite some of the linked list pointers. And if that happens, then you might run into some serious issues with your memory allocator as well. By the way, a lot of these issues can be solved using one of the tools I've created this semester called the heap inspector. And I'll go over that as a at the end of this PowerPoint presentation. So here's what segregated free lists look like. They look sort of like explicit lists that I talked about earlier, except instead of just having one list, you have multiple lists for the different size classes. And size classes are essentially what sizes different allocated blocks. So when a malloc operation happens, it looks into the appropriate list for what size was passed into mmmalloc. So for instance, if I wanted to do an operation, malloc 48, I would not go into this size class, the one that says 32, because this means that it could store anything that's 32 size or smaller. So then it goes to the size class of 64. And it notices, hey, look, 64 is big enough to do a malloc operation of 48. And then it might do something like try to allocate there. If there is no free blocks inside this size 64 list, then it looks into the size 128 list, and it might do the malloc operation here. So essentially, that is one of the more performant strategies. Instead of just having a single explicit free list, you have multiple explicit free lists. You figure out what size classes you need. By the way, again, the memory allocator lecture talks about how to choose different size classes. And in general, I think a 2 to the n approach or like a derivative of that would be appropriate for this project. As long as you tune your size classes to work with the trace files we provide, you should have a performant enough solution. So that is segregated free lists. Another important thing you might want to implement inside of your memory allocator is a check heap function. This is a sanity checker that can print out the blocks in your heap. And you can implement this method to basically debug your heap implementation as errors occur. And remember to just remove this function during testing or submission. Next, we're going to talk about GDB. So GDB is a tool that you're going to use fairly frequently with this project. You can use this to actually do stuff like dumping the contents of the heap out. This is just a short macro you can define in GDB to basically dump the whole heap memory into a file, um, and you could look at it later to see if the heap bytes that are in your heap match with what you expect. But I don't know if I recommend this anymore, since we now have a new heap inspector tool that I'll talk about at the end, which can essentially do the same thing here, but in real time. So another thing you need to think about with this project is the different allocation patterns. So you need to think about like the different workloads associated with Malloc and how they work. For instance, there may be a lot of smaller requests which are short-lived, like maybe Malloc to 16 bytes or 20 bytes or something like that. Or there may be fewer large requests which are held for longer periods of time. So we have a lot of different trace files that test for all of these different possibilities. And if you look through those, you can kind of get an idea as to what we test for when evaluating the performance of your project. Before I continue, does anyone have any questions about anything I just said? And I'll have some time at the end of the session for a short Q&A if anyone comes up with anything. All right, if there's no questions on that section, let's talk about some tools you can use to debug this project. So the first thing we're going to talk about is gprof, which is a tool that you'll probably use pretty frequently when debugging the performance of this project. So essentially, if you add the -pg flag during compilation inside of the make file, this will create a file gmon.out when your code is run. And then you can use the gprof command to check the output of this and see where different functions are essentially being inefficient. It tells you essentially, I think, the execution time of the functions that take the longest to run. And if you look at that, you should be able to see where your code is being inefficient. So remember to use this tool to evaluate performance, but when you're ready to submit, remember to remove this flag. So here's an output as to what the perf utils could look like. So this is, you can see there's an Malloc call here. It says it's taking 4.58 seconds for the whole program. Here's like a percentage of time for each function. This one is eval valid inner. This one looks like it takes 59% of the time. This one, add range, takes 12% of the time. So you can kind of see where most of these performance issues are coming into play. If you see a lot of references to like list next or list end, you may have issues with iterating through your linked list. So be on the lookout for that and make sure that your solution is as performant as it can be with your free lists or your segregated free lists. Next thing we'll talk about to implement your Malloc Lab implementation is structs and bit fields. So when you're starting out on this project, you need to come up with a data structure to represent your free blocks and your use blocks. So one of the things that is also new in this project is something called bit fields. And the bit fields basically allow you to represent one bit inside of your 4-byte boundary tag as whether or not this block is allocated or not. And then the additional 31 bits will be the size of your block, whether that be a free or used block. And if we look into the mmgback implicit file, we can kind of see how that looks inside of the struct boundary tag. So this looks like the first bit is the in-use bit. And the additional 31 bits are the size for the boundary tag. And if you put that into your block, we can use that to essentially make blocks 4 bytes, where I said one of the bits is for in use and the rest of the bits are for size. And that should make it easier for your heap to be more efficient space-wise. So just keep that in mind. Using bit fields is a very good strategy for this project, and you can even copy and paste this struct that we created for you in the mmgback implicit file, if that helps out. So that is bit fields. Anybody have any questions about anything I just said from the previous section?
I have a question.
Sure.
So I noticed in the structs, there actually isn't any kind of footer field. Is this because we don't necessarily know where the footer is going to be located when we're mallocing something?
Exactly. Yeah. So you've noticed that you have your struct block, and then you have your header, and then your payload. So one of the things you need to account for when you're allocating memory for this block, or creating a use block or a free block, is you need to consider the size for the header, the size for the footer, the size for, if you're allocating, then the size of the payload, and then any padding bytes you need to add in to ensure that all of your payloads will be aligned to 16 bytes. But you don't know ahead of time where your footer boundary tag is going to be. So that's why you don't put it in the struct block. Does that answer your question?
Yeah, thanks.
No problem. Any other questions? All right, so let's talk about some logistics. Obviously, please submit code that compiles and test using the driver before submitting. So when grading, all of the tests will be run 3 to 5 times, and if you crash a single time, it's considered failing. That's why I mentioned earlier to use assert statements liberally. So, but I think as long as you pass all the trace files, I think you should be fine. And just run it multiple times and make sure you don't get a single crash. And if all of the tests work, you should be good. The different parts is correctness. So, if your Malloc lab implementation does everything correctly, and then performance, and then there's additional multi-threading extra credit. So if you want to get some free points, implement mmmalloc, mmfree, whatever other operations using a threading approach. I can't remember exactly how many extra points you get for implementing this functionality, but it may be something you want to look into. So here is the breakdown for grading. So the spec will have I think the most up-to-date guide on this. I can't remember if they made any changes between last semester, but essentially it's 100 points total. You get 40 points for correctness, which is the minimum requirement. 40 points single-threaded performance for space utilization and throughput. And then you have 20 points for documentation and code style and Git. Make sure you put at least 5 assert statements in your code. That's one of the things we'll be grading for as well. So we're kind of forcing your hand and putting those assert statements in, which I think is really good. And then, like I talked about, extra credit for supporting multi-threading. So the test driver is simply ran by going into your Malloc lab folder, running make, and doing /mdriver. If you pass in the --help command, you can look at all the different, the --help argument, you can look at all the different flags needed to run the mdriver. There's a bunch of different options. One of them, by the way, that comes to mind that I don't believe we talked about last semester in the help session is -n. -n is a flag that you can use to essentially make the heap always at the same address. And you can use that to hunt down bugs a little bit easier if you want to. So -v is for verbose output. -f allows you to, I think, customize traces. I don't know if that means running a specific trace or something else. And then -s varies the allocation sizes passed into mmfree and mmmalloc and mmrealloc. And so this is the performance. So we have throughput and utilization. Throughput is the number of requests per second, and utilization is essentially how your space utilization is. Basically, how much of space the heap has been expanded by versus the space the user data takes. And you need to consider essentially fragmentation and any overhead inside of your mmmalloc implementation. And that should get you a good utilization score if you take that into consideration. And throughput, by the way, is something you can get with having a performant segregated free list strategy, and you make sure to tune your size classes to be efficient with the trace files we provide. So next, we're going to talk about the trace files. If you look in the traces directory inside of the Malloc lab folder, there are a bunch of files that essentially the test driver runs to perform various different allocations. So the first number is the heap size, the number of unique identifiers, and then the number of operations. I can't remember what this number here is, but every operation thereafter, starting from line 5, are allocate, free, or realloc operations. And the driver will essentially go through this file line by line, performing each allocation in order. And then the M driver will evaluate the speed and space utilization after executing the trace file to ensure that everything is performant. So, by the way, if you want to perform your own tests, you can make your own trace file, put your own allocate and free operations and your own realloc operations in there, and try to hunt down bugs by making your own trace file. So that's how the trace files work. And one of the things I kept referring to was the dynamic memory management lecture. When I post a PDF, there will be a link to it in the PowerPoint, but if you click on this, it'll take you directly to the PDF that talks about all these different strategies. I believe it's lecture Mem 1 if you go into the CS3214 lectures page. It talks about the implicit versus explicit list, and I think it also talks about RB trees and segregated free lists if I remember correctly. It talks about how you can solve different fragmentation issues and how different blocks do get fragmented. And it also talks about coalescing policies. So I talked about that earlier. If you have 2 adjacent free blocks, you might as well coalesce them. All right. Any questions regarding any of that before I go into a demo about the heap inspector? If not, then I will do a demo on this. I'm going to take a quick minute here just to get everything set up, and then we can launch right into it. Now, it's all dependent on if my SSH works. I don't know why my SSH public key is not working. All right, here we go. I'm on Hackberry. Am I still connected here? Let's go to Hawthorne. All right, so like I said, we're gonna do a quick demo on the heap inspector. This is a tool I've been working with Dr. Back on, and our hope is to essentially catch a lot of these errors I talked about early in execution. So hopefully this will speed up the project time for a lot of you guys. In creating this demo, I actually made a derivative of the mmgback implicit file. It essentially defines a bunch of macros, which are common errors you might get inside of your heap implementation. And I'm going to show you how you can use the heap inspector to catch some of these common issues. Can everyone still hear me, by the way?
Yep.
Okay, perfect. So the first thing you want to do, by the way, is you want to make sure you, like I said, you want to clone the Malloc lab repo or fork it or whatever. And then you want to move this file, mmgback implicit.c, into mm.c. And this will let you, by the way, run mdriver and all of that jazz and the heap inspector without actually doing any coding. So once you have an mm.c file, you can simply type heap inspector. By the way, let me make sure that all of these errors are away. Okay. Heap inspector.sh. It'll do a bunch of compiling stuff if you made changes to your code, and then it'll launch right into my heap inspector. Can everyone see my terminal window?
Yep.
Do I need to increase the size a little bit? Okay, so this is the heap inspector. If I type the question mark or if I type H, it'll print out this list of commands you can type inside of the heap inspector. Some of the ones you could do right off the bat is you could type allocate, which allocates a specific pointer, free, or reallocate, or T, which executes a trace file, which we talked about earlier. So these are probably the commands you'll be using to make changes to the heap. And then you have V, which is, I think, one of the more important parts of this tool, which opens the memory viewing tool. And if we open that up, we can see what the different memory operations look like every time when a change is made to your heap. So if we were to look at your MMinit, like I said, this is the provided base code. It does a bunch of operations and it does some changes to the heap. And we may call extend heap to create some memory. And I'm pretty sure this function just calls mem sbrk. Yeah. And then we return. That's all MMinit does inside of the provided MMG back implicit file. So if we go back to the heap inspector, we can see all these different memory writes happen. So this is where the initial fence gets put into place, and this is the memory write and the pointer where it writes to. So this is what the fence looks like. And if we look into the implicit file, this is defined where the in-use bit is 1 and the size is 0. And if you look at the heap inspector, you can kind of see that replicated in this memory write. So that's where the initial fence gets put into play. Go to the next memory write. This is essentially setting the heap list P. This is not a memory write in the heap. This is actually simply setting a global variable heap list P. And then we have a bunch of other operations like setting the fence again. And it, like I said, it's really handy with showing you where the memory writes are. This is where things start getting interesting. So here, I think we set one of our initial blocks. This is in mm.c line 139. And it's inside the set header and footer function. So we set our initial block, which might be hex address 2048 or 0x100. That's the memory write we see. And then we set the, we copy the header to footer. So this is where our header was right here. And then if we scroll down in our heap, by the way, you can jump to the current memory write by pressing the J button. This is where the footer is written to, the 00080000. And another handy thing is it gives you the line associated with the operation as well. And then it sets the fence and returns from mmminit. So that's a brief overview as to how you can use the memory viewer to essentially debug heap problems pretty quickly. If we were to do something like allocate memory, we could do something like allocate hello and then 1024. This should allocate 1024 bytes to the pointer hello. In fact, you can view the current allocations by pressing the L button or by typing live. This will tell you the pointer that you've allocated, the memory address of that pointer, the size in hexadecimal, and the size in decimal. And if we were to go back to the memory viewer, it takes you right back where you left off at activity 8. You see that there's new actions on the heap. And we can go to the next one. This is where we begin the call to Malloc, and I said I wanted to give it 1024 bytes. And if we keep going, this is where we make a change to the block header. And like I said, by pressing J, you can jump to the current memory write. Carrying on, we copy the header to footer like we saw before. This is where the footer is copied to. And this is another header being set here. And if we go through the rest of the options, we return from a call to mmmalloc, and you could see that the heap inspector will highlight all of the allocated blocks in yellow. This is essentially our payload that the user land process has access to writing to. So this is everything that mmmalloc will return to the user and that they have permission to write to. So that's a brief overview as to how you can look over the allocations and such using the heap inspector. If we go back to the main menu, I want to show you something called the heap inspector tool. But before I do that, let me reset all of the heap actions. And then let's press T to open up the trace menu. And this lets you open up a specific trace file. I'm going to go with short1-bal.rep. So let's go to trace file number 11. And here's something you can do that's really interesting. You can step through each trace file action. It tells you what the next action is going to be. In this case, it's going to be a Malloc 2040 operation. Execute that. And then we could do something like go to the memory viewer to watch this allocation happen. So this one says begin call to Malloc. And then we see all of our memory writes. And then if we hop back to the trace file tool, and by the way, I just pressed T, you can use T and V to alternate between the two tools. We can do the next allocation. So let's hop over and do this allocation or free or whatever that was. I think it was a Malloc actually. Yeah, it was a Malloc. And then you can see all the memory writes associated with this one. So this makes it significantly easier, in my opinion, to debug heap problems because you can see every memory write happen in real time. And then we get a free operation. Let's do that one. Begin call to free. And if I press J, it takes us to this as the block that wants to be freed, this one right here. And we already know that this is the boundary tag for this specific allocated block. And then we'll notice that the in-use bet has been set to 0 because it's a free block now. And we can carry on and look at all of the other things that happen when blocks are free. And then it returns and et cetera, et cetera. Let's go back to the trace file viewer. These are all the commands you can use inside of the trace file viewer. And if you press the right bracket, it does all the allocations inside the trace file. And then you can hop over to the memory viewer again and look at all of the allocations and frees that happen. By the way, one of the things I forgot to mention is if you press the H button, you can look at all the different keyboard controls associated with the heap inspector. So be sure to open up the H menu. It'll be your friend when using this tool. Okay, so that is essentially pretty much the what you need to know about the memory viewing tool. There's a bunch of other cool things you can do inside of the command line. You can look at your free lists. In this case, with the implicit list, there are no free lists. So you won't see anything pop up here. You can press G to open up GDB. You can press B to look at the heap bounds. This tells you what the heap bounds are at this point in execution. You can reset the traces, which I demonstrated a little bit earlier. And these are essentially all of the important commands you could run. Now, I'm sure you're wondering, how can I use this to catch bugs pretty easily? So to demonstrate that, I've actually made a couple of edits to the MMG back implicit, like I mentioned earlier. And if I change any of these pointers, I'll be able to trigger some bugs. So the first thing we'll do is invalid pointer. And I'm pretty sure all this does is it tries to write an invalid, it tries to write to an invalid pointer. I think that's what it does, yeah. And if I enable that, get out of the heap inspector, compile it, you could see that instantly, because I'm pretty sure that this code is in the init, but instantly when I open up the heap inspector tool, it immediately crashes and it says the Malloc lab implementation caused an invalid write. A write attempted to take place at this address with this value. Please see the heap inspector tool for more information. And it gives you like a stack trace to where your error might be. It says, in this case, it's mm.c, line 143. And if we hop over to that line, this is where the invalid write happens. It essentially tries to write this value, 1337, to this pointer, 0x13371337, and clearly that's not a valid pointer in your program. So it takes you to this location, and essentially you can still use the heap inspector when it's in safe mode like this. So we can do things like open up the memory viewer and go to the last action, and we can actually see the offending line that causes this invalid write. So clearly this is not a heap address. It's still displaying this information as a way to help students debug. So just be sure to use this heavily when trying to debug errors in your Malloc implementation. So another thing you could do is you could type B, or I'm sorry, S, which comes out with a stack trace, like you saw earlier. If you lost this, so this will help you track down the error easier as well. Let's see if there's any other commands I can go over real quick. This one is not terribly useful to us because the implicit implementation doesn't have any free lists. And then of course there's GDB. If I open up GDB, it tries to find the right stack frame. Here is where the error happens. And we could do stuff like, I think P invalid will work, and that'll just print out the pointer value. And if we quit, it'll take us right back into the heap inspector. So that's like a quick rundown as to a simple error that you can catch using heap inspector. Let's go over some other ones. And I'm gonna do these pretty briefly because it's already 6 o'clock and I know you guys have places to be, but let me demonstrate how this can catch list corruptions, which is another common error inside of the Malloc lab. So by setting this to 1, it corrupts an internal list somewhere. So this is pointing us to an error on line 139. Let's hop over there. And line 139 is basically where it sets the block header size. And you may be wondering, why is this causing a list error? And the reason for that is because when I implemented this code, I decided to check for if any of the free lists were corrupted after every single memory write action. So that context would be able to help you figure out where the error is. And if we hop over to the heap inspector, we might even be able to see where the list was corrupted. And in this case, we can see that interior.next inside of this linked list was set to 0x13371337, which is not a valid pointer inside of our program. So that's why the program crashed. So that is detecting for problems with your free list. Let's go into Malloc overlap. This is essentially where the program will return a pointer in Malloc to basically within a region of the payload. And if that happens, that's an error because you essentially are returning to the user a payload address that directly overlaps another payload. So if I were to enable that flag, you can see that no crash has happened yet, and we've gone through init with no problems. But then as soon as I type allocate 2 pointers, we'll do pointer 1, and then we'll do 1024 bytes, and then we'll do allocate pointer 2, 1024 bytes. We run into an error here where it says, we attempted to write to a region previously allocated. Your code returned a pointer at this address, but a Malloc's region is between this address and this address. This corresponds with pointer 1. So this essentially tells you that your the Malloc operation you just did returned a pointer, but that pointer plus the size overlaps with another Malloc's region, and you need to fix that code. And again, we should be able to go into our heap inspector, and we might be able to see something leading up to this crash. Let's see if we can find anything. Oh yeah, here we go. This is the buggy code I put in. If Malloc overlap equals 1, old pointer equals BP payload, and then this gets returned to the user, and this is when the crash happens. So let's look at the last crash I came up with, invalid read. This is when an invalid read happens in your program. So if we were to do that, and do something like allocate pointer 1, 1024, and then free pointer, This will take us to another problem error. The Malloc lab implementation caused an invalid read. A read attempted to take place at this address. To debug this, you may need GDB. If we go to the stack trace, mm.c245, this will show us where exactly this invalid read happened. So this is our invalid pointer. It tries to dereference that invalid pointer, and this is where the invalid read crash comes from. And I think you may be able to even see this inside of the heap viewer as well. Maybe not. But if you look at this backtrace, it should be pretty reliable in telling you where the error stemmed from. So that is, in a nutshell, how the heap inspector works. Does anyone have any questions about anything I just said? Or any thoughts, feedback, anything else? I would be happy to answer that. Connor says, this inspector is amazing. I appreciate it, Connor. This is a lot of blood, sweat, and tears went into this project. But yeah, this is all good for you guys to use. Make sure that you have the latest repo of Malloc Lab. I think we made a change to it 1 or 2 days ago. I can't remember. So if you forked it a couple days ago, you may want to refork it because we made a quick change. And in fact, if you run it without the change, it'll give you an error. So just make sure you be on the lookout for that. But yeah, I'm really excited to see you guys be successful with this tool. If you run into any bugs, feel free to email me. My email is in the console output inside of the heap inspector, or you can send me a Discord message too, or come to my office hours. Doesn't really matter. Would be happy to help you guys understand this tool and fix any bugs that come along. So any last questions on anything I said about that? Or any questions regarding the Malloc Lab project in general, because I know that was a lot to take in. All right, if there are no further questions regarding any of this, then you all are free to go. Like I said, we are probably going to do another Q&A session sometime next week. I'm thinking maybe early next week, maybe Monday, Tuesday. I'll come up with a good time and I'll make a post on Discourse. And if you all have any questions that you come up with between now and the next Q&A session, keep that down. Feel free to ask us. We'll be there to answer any questions. Or, post in the P3 discussion, make a post on Discourse. When it comes to the heap inspector stuff, by the way, I made a post on Discourse regarding any feedback or any bugs that you may find or any questions regarding the tool. And if you make a post in that thread, I'll be happy to answer it. But yeah, that's pretty much all I got. Thank you guys for attending the help session, and remember to come to the next one if you have any more questions.